Hi guys, this is your next lesson on what we call exponential function and logarithmic functions. We're going to talk about exponential functions first. This is the beginning of chapter 3. An exponential function would be like this one here, y equals 2 to the x, where the exponent is actually the variable. And if we were to try to graph this and put numbers in for x, like -2, -1, 0, 1, 2, 3, we put them in and look at the graph, and I wrote it out for us to save time. If you put a -2 in here, the negative flips it over, and 2 squared is 4, so we get 1/4. 2 to the -1, we'd flip it over and we get 1/2. 2 to the 0 is 1. Anything to the 0 power is going to be 1. Don't forget that. 2 to the 1 is 2, and 2 to the 2 is 4. 2 to 3 means 2 times 2 times 2, which comes out to be 8. If we put them in here, and we can see that if we put a -2 in here, we get a 1/4, very small on the x-axis. If we put a -1 in there, we're getting 1/2, which is just a little bit higher. Always be right here, 1/2 here. At 0, we would get 1. Anything, all of these are going to cross at 0 unless something is added or subtracted to them outside the function, which would move it up or down. At x equals 1, we get 2 to the 1, which is 2. So this crosses at the number 2. At 2, we got 2 squared, and 2 squared is 4. So at 2, this thing crosses up at 4, up there. At 3, we get 2 to the 3rd. 2 to the 3rd is 8, so it'll be way up here, somewhere at 8. And this is what it means when something grows exponentially. You heard about money growing exponentially, or people or populations or even diseases like this coronavirus will grow exponentially. This is sometimes a good thing if it's in your favor, and sometimes a bad thing if you're talking about bacteria in the body or some other virus. We also have, if we added or subtracted a number within the function, this whole pink graph here would move to the left or to the right. In this case, it would move to the right because we're subtracting 3 inside the function. In this case, the whole graph would move down because we're subtracting a 3 outside of the function. And we've seen that in previous chapters. This here is a very interesting number, e. They call this the exponential function. It's what we call a transcendental number, just like pi is a transcendental number. It's a decimal that continues on forever. We could talk about where this came from and where to derive it, but we don't have enough time. I actually did a paper on this in college, and I do presentations, lectures for the Honor Society at OCC when we're back in section, all about this number. What we could do is explore this number and some of its good uses, and here are 2 formulas that help bankers calculate compound interest, where this is the amount. A stands for the amount of the final answer. P stands for the principal. The principal is how much money you actually start with. E is this number, this 2.71828. And if you wanted to get that number up in your calculator, what you could actually do is the E is behind the LN button, and you'd hit second ln, and the calculator is saying e to the what, and you just put a 1 in to find out what this number is, and you hit it, and you'd see that e is that number, that 2.71828. The r in this formula is going to be the rate, the insurance rate, and the interest rate, and this always comes as a percent, and we have to change it to a decimal. And t stands for time. This interest formula tells us that interest is compounded continually. So this is continuous. This is continuous interest. This one is a little different, where the P is still the principal, the A is still the amount, you got 1 plus, R is still the interest rate. N stands for how many times a year, how many times per year is this thing compounded. Compounds. In other words, if the interest is added onto your account every month, this would be a 12. If it was added on every day, this would be a 365. If the interest was added on maybe every 4 months, this would be a 3. Or every 3 months, that would be quarterly. That would be a 4. So this changes depending on how many times the interest is calculated and added onto your account. And again, T is time. Let's take a look at a quick example of both of these. And we will do, I think we're going to do in the book, on page 449, we're going to look at number 54, and then I'll tell you which ones I want you to do. Well, if this is the formula that we're going to use, and number 54 in the book says, and I'll show it to you, it says, find the accumulated value of an investment of $5,000 for 10 years at a rate of 6.5%. If the money is compounded semi-annually, that's twice a year, quarterly, that's 4 times a year, or monthly, that's 12 times a year. And part D says compounded continuously. So there's 4 parts to this question. Let's look at each part. Again, we're going to use this formula. We're going to use both of these formulas. The 4th part of the question, part D, is going to use the first formula, and the other 3 parts are going to use this formula. So let's take a look at what the problem is saying to us, and you can look on page 449 as well. Let's just put some numbers in. They're telling us that we have $5,000 that we want to invest. And then it's saying that we invest it for 10 years, so T is 10. It's telling us in part A that they want to compound this semi-annual, so this is 2, twice a year. And they told us the interest rate was 6.5%, which we have to change to a decimal, which is 0.065. So now we're going to try to take these and put it into our formula to see how this works. So let's see. If A equals P, which is 5,000, that's your principal, what you start with, 1 plus your interest rate, 0.065, over 2, and again is 2, and T is 10 years. So it's this formula right here, where P is 5,000, R is the interest rate, 0.065, N is 2, and then T is 10 years. And very simply, we could just type this into our calculator and figure that out. I'll leave it up to you to type that in and find out what the answer to number 54 is. In the interest of time, I'll save that for you. If you have a problem getting that answer, let me know. For parts, so this is part A. Part B and C are exactly the same. The only difference is the 2 changes in the formula. But part D says, what if we want to compound that interest continually? This is the formula. And if we were in class, I could even show you like how to calculate your car payments before you even go in there, or if you were inherited some money, $20,000, and how long would it take that money to double, and we'll be talking about all those things a little bit. So what would this amount be of this $5,000 at an interest rate of 6.5% for 10 years? And we very simply would type this into the calculator. And I think maybe it's worth it for us to do both of these. Let's take a look. If I type the first one, 54 part A, into the calculator, we got 5,000, right? I'm going to use a parentheses. I'm going to go 1 plus 0.065 divided by 2, close the parentheses, and go to the, and that would be a 20. Can you see that? And if I hit enter, there's our answer, 9479. So this would be 9479 and some change, about 19 cents worth of change. Your $5,000 after 10 years at this interest rate would then become about $9,500. For this one here, if we were going to do this one, again, we'd go 5,000, and we go times E. So we have to go second ln. That's where you find our E button. Make sure you find it on your own calculator, so when you take a quiz, you'll know where it is before the test. 0.065 times 10, because that's what it's telling me to do there. Now if I do that and close my parentheses, this will give me 9577 and 70 cents. Take this problem and do it over again, because what I want you to do on page 449, I want you to try 53 to 56. And this is on page, again, 449. I did 54 for you. You try these problems. Also, what I would like you to do is to look at some of these exponential graphs. Number 2, it says estimate. Now think about this one. They want us to estimate 3 to the 2.4. Well, I know that 3 to the 2 is 9, and I know that 3 to the 3 is 3 times 3 times 3, which is 27. 2.4 is almost right in between the 2 and the 3, a little closer to the 2 than the 3. The number that's right in between the 27 and the 9, you could actually add them together, and that would become, let's see, 36, and half of 36 is 18. So I'm thinking that 2.4, if 2.5 is right in between, 2.4 is, I don't know, I'm thinking maybe 14 or 15. You could actually put this in your calculator and see how close I came to that. It's just an estimate, and you can try some of those on page 448. Some of those estimates, just 1 to 9, the odd ones, and you don't have to get them exact. Not even really going to be on the test, but it's interesting to be able to do that, to see what our next lesson on logarithms is going to give us. And this one here, if we were to do this one, because I want you to try some of the problems also, which is 11 to 17, the odd ones on that same page. So write these down as you're going along. But if we were to make a chart with this, x and y with a 1/3, let's see how this would look. Let's choose some numbers like -2, -1, 0, 1, 2. And let's see what the y values would be if these were the x values. 1/3 to the -2. 1/3 to the +2 is 1/9, 1 squared over 3 squared. But the negative flips it upside down. So that 1/9 would then change to 9 over 1. 1/3 to the -1 is just 1 to the 1 is 1, and 3 to the 1 is 3. But the negative flips it over and we get a 3. Anything to the 0 power is 1. 1/3 to the 1 is a 1/3. And 1/3 to the 2 is 1/3 times 1/3, which is 1/9. If we were to graph these, 1/9 is very small down here for +2. For 1, be 1/3, it would come up a little bit. At 0, we're crossing at 1. At -1, we come up to 3. And at -2, we go all the way up to 9. So we have a graph that looks like this. It's growing, but in that negative direction because of this 1/3. So I'll leave you those to think about and try these problems. I'm going to post another one soon on logarithms. Good luck. I'll talk to you soon. Most of you did pretty well on your first quiz. So I'll talk to you soon. There'll be another quiz next week, same time.